So now, given any random variable, if its variance is 0, by Chebyshev's inequality, we prove that it has to just be a constant, and its constant is just, the constant value it takes is the value of its mean. Okay, so weak law of large numbers. Now, what the weak law of large numbers says, or basically what the law of large numbers talks about, is if I have x1, x2, I have a sequence of the independent random variables and they're all identically distributed. So you can think of x1, x2 as the values that, as samples from some huge population. Okay? So if you're sampling from a certain population, so they're sampling from the same population, that's why they have the same distribution, and I'm going to sample it so that they're done independently. All right, so these are what you call IID, that's independent and identically distributed. And what the theorem says, law of large numbers, it says if I take the average of this. So n is getting larger, so I'm taking a larger and larger sample and I take an average. I denote them by capital X1, capital X2 because I haven't yet actually observed what values I get. So this is, theoretically speaking, if I draw a random sample, as the sample size n gets larger, I take the average value of that. This is a random variable, and this random variable will become a constant as n goes to infinity. And the constant mu is going to be the common mean for all of these. Okay? So mu is mean of the distribution. Of the distribution, there's only one distribution I'm sampling from. So mu is expected value of xi for all n, because they're sampled from the same distribution. So this random variable, as n becomes very large, just becomes a constant. So it means that if I actually observe values of xi's, and I compute the value that I get, for very large n, the value that I get will be very close to mu. Because I know that in theory, in probability, this approaches just as constant. It becomes a constant mu. So any realization of this random variable, that is, any particular observation of the random variable, will be close to mu. All right. And this is very important because this is what our whole theory of, well, a big part of the theory of statistics is based. That is, why do we bother taking a large sample to estimate this mu value? And that's basically because of the weak law of large numbers. We know that if I take a large enough sum and take the average of that, it will start approaching the distribution mean value. Okay, so let's write down the actual statement of this theorem. The sequence of independent and identically distributed random variables each having this is the common mean, mu. Then for any x greater than 0, probability that the distance of this average sum from mu, probability that is greater than or equal to epsilon, goes to 0 as n goes to infinity. So probability that this distance is greater than epsilon becomes 0, so that means there's no distance between this and mu. So let's look at this So I don't know what the distribution of this is, but what is the mean of this at least? Let's use the properties of expectations, 1 over n, expectation of the sum, xi, and I can interchange summation and expectation. Summation I equals 1 to n mu n. So I know that the mean of the sum of this average is also just mu. What about the variance of the sum? Let variance of xi be denoted by sigma squared. So let sigma squared be the common variance. Then what is the variance of this average random variable? Now I know from the properties of variance, if I have a constant times a random variable, when I pull the constant out, it gets squared. So I have 1 over n squared, the variance of this random variable. That was one of the properties of variance. If I have a times x, the variance of a times x is a squared variance of x. So this is my random variable, and I'm dividing it by a constant. If I pull the constant out, it's 1 over n squared. And xi's are independent. What do I know about the variance of sum of independent random variables? It's just the sum of the variances. So it's 1 over n squared, sum I equals 1 to n, variance of xi. This is 1 over n squared, n times, and variance of xi is sigma squared for all n. So I end up with sigma squared. So we did this earlier, and this is already a hint as to why we get the statement of this theorem, that this average approaches a constant. Because you see, the variance of this random variable is sigma squared over n. As n goes to infinity, the variance is becoming 0. And what do we know about random variables with variance 0? They're constants. Okay. Constants with value equal to the mean, so that's why this should be its mean. Precisely, we use Chebyshev's inequality. So the probability xi equals 1 to n xi n minus mu. The distance of this is greater than or equal to epsilon. This is bounded by the variance of this over epsilon squared. That's the Chebyshev's inequality. Chebyshev's inequality says the probability of random variable minus its mean greater than or equal to something is bounded by the variance of this random variable divided by epsilon squared. That was the statement of Chebyshev's inequality. And our variance of this, we just calculated that. That we know sigma squared over n over epsilon squared. So then this is sigma squared over n over epsilon squared. So keeping epsilon fixed, if I send the limit as n goes to infinity, bounded above by this, and this goes to 0, That's not equal to 0. So that's just a statement of your weak Laplace number. Okay, so in the exam, I mean, you're not going to be tested on the weak Laplace numbers. There's nothing more that you could say other than, well, you know that the average of this is going to approach mean. So it's just something for you to be aware of because it's a very important theorem in probability. All right, but you will have a problem on Chebyshev's inequality. So I could ask you to get a bound on certain probabilities using Chebyshev's inequality. If I also give you the distribution, I can ask you to compute the action probability and compare it with the bounds you've got. And yes, so with Chebyshev's inequality, that's all we talk about. All right. Let's talk about what problems we
You have Anna?
no, but I'm going to post it online. I made a list of problems.
So, examples so much.
I'm sorry?
Examples so much of other readings.
I'm sorry? Yes.
He's asking if the exam will be similar to what you're giving us, but you're just giving us more recent stuff, right? Or are you giving us kind of like...
No, these are just problems from... So, the final exam is not cumulative. Other than if there is something from the later chapters that depends on something from the early chapter, then of course you need to know that.
Right.
But you're going to be tested, so the final exam syllabus is basically chapters 6, 7, and 8.
Okay.
Is everything from those chapters. You have from chapter 6 so section 6.1 is just so basically you have everything from joint distributions onwards. So section 6.1 introduces joint distributions. I will not give you anything involving more than 2 random variables. Okay, so it's going to be the joint distribution of 2 random variables, and so that's basically it. So discrete and continuous joint distribution of 2 random variables. So joint distribution of 2 random variables.
You said discrete, yeah?
Yeah, but discrete and as well as continuous. But only 2 random variables, the joint distribution. So if you're looking at examples, you can look at everything in the book to page 239. This is still page 239 in section 6.1. If you want to read examples in the book, you can do that. Section 6.2 is independence. Section 6.2 showing that 2 random variables are independent or not when I give you their joint distribution. So here, if you want to read examples, you can read till including example 2c. in section 6.3, which is the sums of independent random variables, I'd say just stick with my notes. So that, I just say, so it includes section 6.3.1 and 6.3.3, 6.3.4. Section 6.4, that's conditional distribution. Discrete case, continuous case. Okay, so section 6.4 to example 4b. And 6.5 to page 267. That means including page 267. Skip 6.6. The 6.7, only look at my notes. The book does it slightly differently. There's a method involving calculating determinants, the Jacobian, and something like that. So just look at that's a joint distribution of functions of random variables. So this, for example, would be something like, I give you the joint distribution of x and y, and I define a new random variable z as, say, x squared plus y, and I ask you to find the density of z. This kind of thing. And basically the method was, you find the distribution function of z, that's probability z less than or equal to z, probability that x squared plus y is less than or equal to z, and then you integrate over the region x squared plus y less than or equal to z, you integrate the joint density function. And then once you find your answer should be in terms of this number, this z, del z, differentiate with respect to little z and every density function. So that's the method I want you to look at. So with that finishes chapter 6. And chapter 7 so 7.4, that's covariance, variance, sums, and correlation.
Seven point what?
7.4.
Oh, we don't even need sections 1, 2, and 3 very much.
So for 7.4, read till the end of page 328. So chapter 7, 7.4, so page, what is it? 328, 398, and 28, and you can exclude example 4C when you're reading through that section. So only through page 328, even within that you can exclude example 4C. Then 7.5, we have all of 7.5.1, 7.5.2, 7.5.2 till example 5D on page 335.
Nothing from 7.1 to 7.3.
No.
Tell, 5D, that was SD. Okay.
So 5D on page 335, and then 7.7, page 354 to page 360. So page 60 to example 7H. And then finally, chapter 8, 8.1, 8.2. 8.1 to everything.
That's page 359.
5, oh, that one.
For 7.7?
359 probably,
7.7,
or, I don't know.
350.
3
354.
4.
Yeah. 360. And 8.3. Exclude theorem 3.2. So that's a different version of the central limit theorem where you don't require identical distribution. All right, okay, so this tells you exactly what you can look at in the textbook. You want to look at some extra example problems, you can read through what's in the textbook. So read this, read your notes, look at all your homework problems again. I think some of you got last week's homework problems wrong, so if you want to discuss that on Wednesday, we can do that. And I'm going to put these list of problems online, and you should start working on them. All right, well, what's the time right now?
5 o'clock.
Okay, we can start doing problems right now.
Is there any additional, like, chapter problems that we should type the homework ones?
Okay, how about I first assign these problems to
Do
you guys
those first, okay.
these first, and then let me look at some of the problems that